In this video, we're going to take a look at doing calculus with parametric equations. In a previous video, we looked at parametric equations, how to graph them, and how they relate to our standard rectangular equations where we have y and x and y coordinates. So we want to do calculus with parametric equations. We're not going to do every single topic that you've ever done in calculus, but we'll do a few different calculus topics with our parametric equations. Now the question is, why would we want to do this? Well, obviously, if we're already dealing with parametric equations, then doing the calculus with the parametric equations themselves allow us not to have to convert back and forth between rectangular and parametric form. Another reason why we might want to do calculus with parametric equations is that sometimes the calculations are easier to deal with. And so in parametric equations, maybe the calculations are easier to deal with than they would be in rectangular coordinate systems. And this is especially true when we're dealing with non-functions in the rectangular coordinate system. When I can't write y is equal to a function of x, but I have a nice parametric form, then a lot of times it's easier to deal with the parametric equations. Now, the first thing we're going to look at is the derivative, or in this case, we're saying the first derivative. Assume that we have a smooth curve, which we'll call C. And this curve is a parametric curve. So we can get the x value using x is equal to a function of t, and we can get the y value as y is equal to a function of t. Normally, when we think of the first derivative, we think of it as change in y over change in x. And that is the instantaneous rate of change, dy over dx. Well, if y is a function of t, then I can find the rate of change in y with respect to t by just taking the derivative of y with respect to t. And the rate of change in x I can think of as the derivative of x with respect to t. Now this works so long as that derivative of x with respect to t is non-zero. If it is zero, then obviously we are not defined at that location. So if I want to find dy over dt, that's essentially the slope of our tangent line in rectangular form. Then I can just do derivative of y with respect to t divided by derivative of x with respect to t. Let's take a look at this example. Here we have a pair of parametric equations. X equals t squared plus 4t, and y equals 2t to the third plus 7t plus 8. I'll find the first derivative of this pair of parametric equations. Again, I'm thinking of it as derivative of y with respect to x is the same as thinking of instantaneous change in y over instantaneous change in x. I do those each with respect to t. So essentially, I'm going to take the derivative of my y function. That is going to be 6t squared plus 7. And divide that by the derivative of the x function, which is going to be 2t plus 4. Now, this is going to exist as long as t is not -2. When t is -2, this derivative obviously does not exist because we get a 0 in the denominator. But that's it. That's the whole thing. That is my derivative. And this will give me slope of a tangent line. So imagine I plugged in the number 0. And by 0, I mean t of 0, just so that we're clear. The derivative with respect to x at t of 0 would be 7/4. That is the slope of the tangent line. And it's the slope of the tangent line at point well, the x value can be found by plugging in 0 for t in this equation. So the x value is going to be 0. The y value can be found by plugging in 0 into this equation. So the y value is going to be 8. So at the point 0, 8, we should expect the slope of the tangent line to be 7/4. Let's graph this parametric equation, this parametric curve, and then look to see if that matches up with where we think it should match up, or how we think it should match up. So the equation, this parametric set of equations gives me this graph here. Obviously, we're looking at the point of 0, 8. Let me just highlight that point. And so what we're saying is that the first derivative, remember first derivative indicates slope of the tangent line, is 7/4, which means that the instantaneous rate of change at that point is 7/4. By the way, if I graph the actual tangent line, it's going to have slope 7/4 and go through the point 0, 8. So you can see that we do in fact get the right slope. It does look like we're traveling in the correct direction. So that's the tangent line. And again, first derivative gives me slope of the tangent line. Now you may ask, I noticed that we could not plug in -2 into the first derivative. I mentioned that. Well, the reason why we can't plug in -2 into the first derivative is because if I plugged it into the function or to the xy values, I'd be at the point -4, -22. And what happens with this, excuse me, with this graph is that it curves as you move towards the left. It starts from top to bottom, starts moving towards the left, and then at the point -4, -22, it actually turns back and starts moving to the right. So the reason you can't plug that in is that at this particular point, that's the point you get when you plug in a t of -2. At that particular point, we have a vertical tangent line. X equals -4 is the tangent line in that scenario. So x equals -4, this vertical tangent line happens. And obviously, the slope of a vertical line is undefined, or some people would say infinite. And therefore, we can't calculate anything at that particular point. We can't calculate the first derivative at that particular point because I end up having a vertical tangent line. Again, slope is undefined on a vertical line. Let's do another example. Let's find the derivative of the hypotrochoid that we looked at in it was one of our interesting parametric graphs that we just glanced at and saw in the parametric equations video. So we have x equals 2 cosine t plus 5 cosine of 2t over 3, and y equals 2 sine of t minus 5 times sine of 2t over 3. If we're looking at this algebraically, derivative of y with respect to x, my normal slope of tangent line, I'm just going to set that up as a fraction. The top of that fraction is the derivative of y with respect to t. In this case, if I took the derivative of y with respect to t, I would get 2 times the cosine of t minus 5 times the cosine of 2t over 3. And then I would have to multiply times the derivative of the inside function. The derivative of the inside function is 2/3. So 5 times 2/3 gives me 10 over 3. That's just the numerator. The denominator, well, the derivative of cosine is negative sine. So we'd get -2 times the sine of t plus 5 times the derivative of cosine, which is negative sine. So I'm going to change that to a minus out front. Minus 5 sine of 2t over 3 multiplied times the derivative of the inside function, which is 2/3. So 5 times 2/3 gives me 10 over 3. This is the derivative of the hypotrochoid. So for any value of t that doesn't lead to a 0 in the denominator, I can find the slope of that tangent line for any point on the hypotrochoid. Remember, the hypotrochoid was this star-shaped graph. That's what was going on. And basically, now we can say, no matter what point we're at here, as long as the denominator is not 0, denominator is actually going to be 0 right here when t is 0, because I can see that because I should get a vertical tangent line. But at every other point where we don't have vertical tangent lines, we can find the various slopes of the tangent line using that formula that we just saw. Now, obviously, this is really nice for this example because this would not be a function in terms of y is equal to a function of x. There's no way I could have drawn it that way. And so this hypertrochoid, this is by far the best way to get slopes of tangent lines for points on there. That was also true in my previous function, or my previous curve. This was not a function either. All right, you can see it's not a function because it fails the vertical line test. So in the previous example, this was also a very good way to find first derivatives. Once we've done first derivatives, then doing second and third derivatives is pretty straightforward. Now, it's not as straightforward as you might think. You cannot take the derivative of y twice and divide it by the derivative of x twice. That's not going to work because the second and third derivative, like the second derivative gives you concavity. The second derivative is the derivative of the first derivative with respect to x. So what I have to do is I'd have to take my first derivative that I just found, which is going to look like that fraction, take a derivative of that, and then divide by derivative of x with respect to y. For my third derivative, again, derivative of the third derivative of y with respect to x, I'd have to take a derivative with respect to x of the second derivative. And in order to do that, I take a derivative with respect to t of the second derivative divided by the derivative of x with respect to t. So it's always the derivative of the previous one divided by dx dt. Let's take a look at this example. We'll find the first and second derivatives of the following set of parametric equations, and then we'll find the derivative values when t is equal to 3. Excuse me, when t is equal to 3. If you want to try this on your own, feel free to pause the video and try that on your own. Now, this one is pretty straightforward. It's an easy calculation. The derivative of y with respect to t is 3. The derivative of x with respect to t is 4. So my first derivative is just the constant of 3/4. Now, my second derivative, that is the second derivative of y with respect to t, is going to be, I'll write this one out, it's going to be the derivative with respect to t of the 3/4 that I just found. And then I divide that by dx dt. Now, in this case, the derivative with respect to 3/4, the derivative of t with respect, the derivative of 3/4 with respect to t is simply 0. But in the denominator, I would get a 4. That's the same 4 I got in the previous denominator. I take a derivative of the x function with respect to t. Now, what's going to happen when I plug in a t of 3? Not much. This is a constant. This is also a constant. So when t is 3, the first derivative is 3/4. When t is 3, the second derivative is 0. That would have also been the case if t was 123 or 129 or negative 129. Since first derivative and second derivative are constant, no matter what you plug in for t, you just get those numbers. 3/4 for the first derivative 0 for the second derivative. By the way, the reason you would get a first derivative that is constant is because when you graph this pair of parametric equations, you get a straight line. So you get a straight line, and lines, as we know, have constant first derivatives. Here's one where we don't get a straight line when we graph it. So let's find the first and second derivatives of the following pair of parametric equations, and then find the first and second derivative values when t is equal to 6. Again, if you want to push pause and try this on your own, feel free to do that. All right, so let's take the first and second derivatives of this set of parametric equations. First derivative, that is dy with derivative of y with respect of x, first derivative. Again, all I'm doing is taking the derivative of the y function with respect to t, which in this case is 1/2, or I'll write it as 0.5, divided by the derivative of the x function with respect to t. That would be 2t. So if we do this, I can simplify that as 1/4t, or 1/4 times t to the negative 1 power. Again, that's just a little simplification because I kind of know what's going to come up. When I do my second derivative. My second derivative is second derivative of y with respect to x. We're taking the derivative with respect to x twice. So what I do is I take the derivative with respect to t of my first derivative, which is 1/4 times t to the negative 1 power. And then I take dx, or dt. In other words, the derivative of x with respect to t. In this case, well, derivative of x with respect to t, I'll do the denominator first. That's, again, just 2t. The derivative of the numerator is negative 1/4 times t to the negative second power. You can write that a lot of different ways, but the way I'm going to write it is a single fraction. T to the negative 2 power on top is like a t to the third on bottom. And then we have 1/4, and then we're dividing by 2. That basically means I have an 8 in the denominator. So negative 1/8 times t to the third. That 8t to the third is all in the denominator. That's the second derivative. Again, if you wanted to write the first derivative in that same fashion, you just write 1/4t if you wanted to do it that way. So there we go. Now, when t is 6, we'll just state this. When t is 6, then we're at the point, well, what do we get when we plug in 6? We're going to get 6 squared minus 4. That's 32 for the x value. And 6/2, that's a 3 for the y value. So 32, we're at the point 32, 3. Sorry, 32, 3. And the first derivative at that point, some people, well, you can write it in a number of different ways. If you write it like this, you can Some people write a vertical line and say when t is 6, what do we get? Well, just plug this in. 1 over 4 times 6 is 1/24th. That would be the slope of the tangent line at that point. The concavity, well, let's again say at t equals 6 would give me -1 over 8 times 6 to the third. 8 times 6 to the third is 1,728. So I get -1 over 1,728. So very close to zero there. Very close to kind of straight looking there. Let's just graph this to see what's happening and kind of confirm what's going on. So I've graphed that. Obviously, the graph of this parametric set of equations gives me a parabola pointing to the right. And at the point 32.3, we're out here. If you zoom in to that, what we're saying is that the slope of the tangent line at this particular point should be 1 over 24. That would give me y minus 3 equals 1 over 24 times x minus 32 as the actual tangent line. And notice that that tangent line does look like it's going in the correct direction. In fact, these lines that I have drawn are so thick that when I click on the curve, I can't actually see the tangent line until it's far away. And if I click on the tangent line, it dwarfs the curve because it's until we're pretty far away. So that's the tangent line. And obviously the second derivative gives concavity. It's pretty close to linear looking at that particular value. And so we get something that looks pretty close to zero. But it is sloping in just slightly, a -1 over 1,728, sloping in slightly. One other thing that we can do when I have a equation for the first derivative is I can use that equation to find all points or all t values which give me vertical tangents or horizontal tangents. Remember, a vertical tangent is happening when we get the form some number divided by 0. And a horizontal tangent will be when my tangent is 0. Now, we've already found the first derivative. It is 1 over 4t, 1 over 4t, where 4t is the denominator. So if I want a horizontal tangent, that happens when the derivative is 0. Obviously, in this case, 1 divided by 4t, no matter what value you make t, you're never going to get a 0. So this has no horizontal tangents. Nothing, we're going to get no solution there. So no solution when I set 0 equals 1 over 4t. So no horizontal tangents. On the other hand, the horizontal tangent, excuse me, works differently from the vertical tangent. Vertical tangents happen when the derivative has form, some real number, I'll call it a, divided by 0. Our derivative is 1 over 4t. We can get that when t is 0. So basically we're asking, when is 4t equal to 0? 4t is equal to 0 when t is equal to 0. So we get a vertical tangent when t equals 0. And by the way, if we remember what our original equations were, that means we'd be at the point -4, 0. When I plug in t of 0, I get -4 for x. When I plug in t of 0, I get a 0 for y. So -4, 0 would be where I have a vertical tangent. Hopefully that makes sense. Just for the sake of looking at this, or just for the sake of going through it, notice again at the point -4, 0, it does look like, since we're turning there, does look like I should get a vertical tangent. And obviously, there's no horizontal tangents because we're always growing, although be it at a very slow rate, or in here, we're always declining on the other side, again, at a very slow rate. So one vertical tangent, no horizontal tangents in this case. Let's do those same calculations by finding let's do the same concept. Let's find the first and second derivatives of the following pair of parametric equations, and then find values when t is 0. We will not find vertical or horizontal tangents for this one. I'm going to jump right into it. If you want to, you could push pause if you want to do it on your own. So first derivative. Derivative of the y function with respect to t is the exact same thing as just the y function with respect to t, because the derivative of e to the t is e to the t. Derivative of x with respect to t will be 20. And I'm going to rewrite that because 1200 is very easy to divide by 20. So we get 60 e to the t. The second derivative of y with respect to x is going to be, again, I'll write the steps. I take the derivative with respect to t of, in this case, it'd be 60 e to the t power. And then the derivative with respect to t of the x function, I'll just call that dx dt. In the numerator, we would get 60 times e to the t power. In the denominator, I would once again get 20. I'm going to simplify that to 3 times e to the t power. So that's my first derivative. That's my second derivative. If I want to find these things at 0, in other words, when t is equal to 0, then I can do that fairly efficiently. Notation here does the following. Derivative of y with respect to x at t equals 0 is going to be 60. When I plug in 0, e to the 0 power is 1. 1 times 60 is 60. And then when I do the second derivative with respect to x at t equals 0, I'm going to get the number 3. So this, again, tells me concavity. This tells me slope of the tangent line. We could do a third derivative as well if we'd like. If I wanted to do the third derivative, I just take the derivative of 3e to the t. In fact, we haven't done one of those yet, so let me just do that. What I would do is I would take the derivative with respect to t of the second derivative. So derivative with respect to t of 3e to the t power, and then divide that by dx dt. So that would be 3e to the t power divided by 20, or if you want to rewrite that, 3/20 times e to the t power. So there's my first, second, third derivative. If I plugged in 0 into my first derivative, I get 60. If I plug in 0 into my second derivative, I get 3. Obviously, if I plug in 0 into my third derivative, I would get 3/20. So that's how we find the first and second derivatives, and you could go on and on and on. If you wanted to find the fourth derivative, the fifth derivative, you could do the same approach. If I'm doing derivative of the third derivative, I take the derivative with respect to t of the second, divided by dx dt. It'd be the fourth derivative, I'd take the derivative with respect to t of the third derivative, divided by dx dt. And so on, and so on, and so on. Let's do this example. This is example 6, finding the first and second derivatives of x equals secant of t plus 2, y equals 2 times tangent of t plus 1. In the previous video where we looked at parametric equations, we know this is going to give us a hyperbola of some sort. So this is finding the first and second derivatives of some given hyperbola. As always, if you want to try this on your own, you can push pause on the video. The first derivative that we calculate is going to be the derivative of 2 times tangent of t plus 1. Now, the derivative of tangent is secant squared. So if I take the derivative with respect to t, it is going to be 2 times secant squared of t, and then the derivative of 1 becomes 0. The derivative of the x, well, secant has derivative, which is secant times tangent. So the derivative of x is secant of t multiplied times tangent of t. And then derivative of a constant is just that. Clearly, I can cancel out some things. Remember, secant is 1 over cosine. I can cancel out one copy of secant. That's pretty clear. I can cancel that out on the numerator and denominator side. And then secant is 1 over cosine. Tangent is sine over cosine. If those cancel out, what I get is 2 over the sine of t when those cancel out. Or in other words, 2 times the cosecant of t. That's the easiest way to think of it, 2 times the cosecant. When I do a second derivative of y with respect to t, with respect to x, excuse me, I am going to do the same thing that we always have done. Derivative of x with respect to t on bottom, and then I'm going to take the derivative with respect to t of the first derivative piece, which is 2 times the cosecant of t. Cosecant has derivative, which is negative cosecant times cotangent. So I get negative 2 times cosecant of t times cotangent of t. And derivative of x with respect to t is secant times tangent once again. If I wanted to stop there, I could. I'm not going to. Secant is obviously 1 over cosine. So what I could do is, since secant is the reciprocal of cosine, I can rewrite this as negative 2 cosecant of t multiplied times cosine of t multiplied times cotangent of t. And then the reciprocal of tangent is cotangent. So I can multiply times another cotangent of t. If I just say, instead of dividing by tangent, I'm going to multiply by its reciprocal. Instead of dividing by secant, I'm multiplying by its reciprocal. By the way, cosecant is 1 over sine. So we get cosine over sine, which is cotangent, times cotangent times cotangent. So this second derivative is actually cotangent to the third power of t. I'm sorry, negative 2 times the cotangent to the third power of t. Negative 2 times the cotangent to the third power of t. So that's my first and second derivative. And this is of the hyperbola given here. Now, other hyperbolas would obviously have different first derivatives, would have different second derivatives. I just want to point out that this first derivative, there are ways to get the denominator to be 0, but there's not any way to get the first derivative to be equal to 0. So this hyperbola is going to have vertical tangent lines at a couple of places, but it's not going to have any horizontal tangent lines. And if you think about that, that means this hyperbola, since it can have vertical tangent lines, is going to have to point right and left. no horizontal tangent lines. We'll clear that out. Let's take a look at another example. This is the example of an ellipse, and we're tasked with finding the first and second derivatives of this ellipse. So the first derivative and the second derivative of the ellipse given by this pair of parametric equations. Again, if you want to try this on your own, push pause on the video. In a couple of seconds, I will show you how this is done. All right, first derivative, meaning the derivative of y with respect to x. I always start out by taking the derivative of y with respect to t. That's going to be 2 times the cosine of t. And I divide that by derivative of x with respect to t. That's going to be -5 times the sine of t. Now, I could leave it like that, but for the sake of the next step, cosine over sine is cotangent. And I'm going to rewrite that as cotangent for the sake of finding the second derivative, because it'll be easier to find the second derivative if I write it that way. So let's take a look at the second derivative. I'll take a derivative with respect to t of -2/5 times the cotangent of t. And then divide that by the derivative of x with respect to t, which we already know. The derivative of cotangent of t with respect to t is going to be a negative cosecant squared. If I do a negative of a -2/3, I get a negative of -2/5, I get a +2/5 times the cosecant squared of t. Derivative of x with respect to t is the same derivative of x with respect to t I had above. That's -5 times the sine of t. Remember, cosecant is 1 over sine. So actually, if I multiply it by the reciprocal of sine, I get cosecant to the third. And then 2/5 divided by -5 is 2 over -25, or -2/25. So if I simplify this as much as I can, then it is -2/25 times cosecant to the third of t. By the way, you can see that in this ellipse, there are ways to get the numerator to be 0. There are ways to get the denominator to be 0. And therefore, we're going to have both vertical and horizontal tangent lines, which should make sense because when we take an ellipse, the endpoint of the major axis, the endpoints of the major axis, the endpoints of the minor axis will give me either horizontal or vertical tangent lines, depending on if my ellipse is stretched out more in the x direction or more in the y direction. but I'm going to get two horizontal tangent lines, two vertical tangent lines. So we get both vertical and horizontal tangent lines there. Second derivative looks pretty wild, but that's just what it is. So we have calculated a lot of first and second derivatives, and we've used that formula here and here. We've done 1/3 derivative, but this is the basic formula. Derivative of the function of my y with respect to t divided by dx with respect to t, derivative of x with respect to t. That always works so long as the denominator is not 0. Second derivatives and third derivatives work very similarly. So now let's take a look at another really useful tool with parametric equations, and that is arc length with parametric equations. Remember that parametric equations are really good at tracking movement over some curve. So if we're tracking the movement over a curve, then the distance our point travels is something that we would like to track. So it's good at tracking distance, and the distance our point travels is going to be an arc length of that curve. I'm not going to go through all of the details to where this arc length formula comes from, but I will give you a general idea. We've dealt with arc length before in a previous video a while back, hopefully. And essentially, what we do is we create a bunch of little straight line chunks, and then we let those straight line chunks get smaller and smaller and smaller. And straight line distance is square root of a squared plus b squared, where a and b are the legs of a right triangle. And if you think about a right triangle, you can think about a as the x value. So the change in a is going to be the derivative of the x value, which in this case, since we're dealing with parametrics, is the derivative of f of t. So that's like a squared plus b is going to be the change in y. So that's going to be a derivative of the y function. In this case, we're calling that g of t. And we take smaller and smaller chunks, add them up, and then integrate. Now, I used a and b as poorly as I could probably, but the point here is that the arc length formula is the integration of, let's start at t value of a and go to t value of b of the square root of f prime squared plus g prime squared with respect to t. Again, be careful, a and b here in this formula are the values for t, not just the Pythagorean theorem I was talking about earlier. So a and b are the values for t. Let's do an example of this. We want to find the arc length of a curve on a given interval. Our curve is given by the parametric equations x equals 3t minus t squared and y equals 2t to the 3/2 power. We want to find the arc length on the interval where t is between 1 and 3. Now, before we move on, well, before we start going to fast here. I want to just say that arc length is usually denoted by a lowercase s, so that's why we use that. In our case, it's pretty easy to see that the bounds on t should go from 1 to 3. So a in this case is 1, b in this case is 3. Then I have to take the derivative of my f, which is the derivative of the x function. I am going to use some kind of poor notation, not great notation. X prime of t is the notation I'm going to use, and that is going to be 3 minus 2t. That's the derivative of x with respect to t. The derivative of y with respect to t is going to be 3 halves times 2 is 3 times t to the 1/2 power. So those are my derivatives. And it's the derivatives that I put into my arc length formula for f prime and g prime. So 3 minus 2t would go in for my f prime. 3 times t to the 1/2 power would go in for my g prime. If you wanted to simplify this, you could. You could rewrite that. If you wanted to try that using by hand, you could. Since it's a definite integral, I am just going to punch it into my calculator like we've done a lot of other times before. So when you're integrating with respect to t, it's just like integrating with respect to any other variable. You can use and replace t with any letter you want. So if you want to use the x, you can. You could have also changed the mode on your calculator to parametric mode, and then every time you hit the variable key, then it actually gives you a t. I might provide a link to a video on that. When we get the arc length, I got approximately 8.86 as the arc length from t equals 1 to t equals 3 on this curve. The curve, the parametric curve for this pair of parametric equations. And that's it. That's the whole arc length. In example 9, we have a set of parametric equations that we've done before and that we've dealt with before. And we're going to find the arc length of that curve from t values between -2 and 2. This was the parabola pointing right. And so we're going to find the arc length of that parabola from t values of -2 to +2. In this instance, what we'll see is, or what we do see, we have to take the derivatives. X prime of t is actually 2t. And then y prime of t, the derivative of y with respect to t, that is going to be just 1/2 or 0.5. So the arc length formula is going to become an integration from -2 to +2. The first derivative of the f of t, that's the derivative of x with respect to t, is going to be 2t. And then the derivative of y with respect to t is 0.5. And that's what we get. So we get the integration of square root of 2t squared plus 0.5 squared integrated from -2 to 2 with respect to t. Plug that into your calculator, or if you want, you could do it by hand. Doing it by hand is not is doable. It's not the greatest, but it is doable. And you'd have to use some trig substitution, I believe. I got about 8.41 as the arc length from -2 to +2. This was that same curve. So again, if I take the t value from -2 to +2, I just found the length of that section. So if somebody were to, one point were to move along this section, how long would they have walked? They would have walked 8.41 units. That's the length of that section of this curve. Let's do another. Let's find the arc length of this pair of parametric equations on the interval from 0 to 2 pi. That is, t values between 0 and 2 pi. If you want to try it on your own, go ahead and push pause on the video. In this situation, again, I always take that derivatives. Derivative of x with respect to t is going to be -5 times sine of t. Derivative of y with respect to t becomes 2 times the cosine of t. When I put that into the formula, I get integration from 0 up to 2 pi. And we're integrating the square root of quantity -5 times the sine of t squared plus 2 times the cosine of t quantity squared. I am not going to do that by hand. That would be pretty tough to do by hand, but I will punch that into the calculator. By the way, just as a note, when I punch this into my calculator, I need to make sure that my mode is in radian form because we're going from 0 to 2 pi. Our angles there are in radians. And every time you do calculus, it's pretty much in radians, pretty much. So type that into the calculator. As I am doing that, and I have done that, it's going to take a minute to calculate the actual value, but I get about 23.01. So about 23.01 as the arc length of this curve. Now remember, this curve was the curve for an ellipse. And if you go from 0 to 2 pi, that is one time around the ellipse. Therefore, this is the perimeter of the ellipse that we looked at earlier. So the 5 cosine of t minus 1 as your x value, 2 sine of t plus 3 as your y value ellipse. So this ellipse has perimeter, which is about 23.01. There we go. Once we've calculated arc length, then that is a short jump to surface area. If I want to revolve a curve around the x-axis, what I do is I start with my arc length formula and I multiply by 2 pi r. Now, if we're revolving around the x-axis, then the radius is going to be the y value. And I'm using the same notation I did in the previous section where y is a function of t called g of t. So if we're revolving around the x-axis, I can simply take 2 pi, integrate from a to b. The g of t, that again, think y, times the square root of the derivative of x squared plus the derivative of y squared. And if I want to revolve around the y-axis, I just do the almost the same thing, but instead of multiplying by g of t, now I multiply by f of t. By the way, this is the normal f of t. This is not the derivative. The same is true here. This is g of t. This is not the derivative. Once we've seen that, then we can find surface area for revolving any curve we want around, well, the x-axis or the y-axis. If you wanted to revolve it around another horizontal line or another vertical line, you just shift the radius. So let's find the surface area generated by revolving this curve, that parabola, around the x-axis. And let's do that over the interval from t values from 0 to 2. Now we've already found the arc length, so we've actually already calculated the derivative of x with respect to t, derivative of y with respect to t of this same curve, of this same parametric curve. We did it over a different interval when we found the arc length, but none of those steps are gonna change when we deal with surface area. When we deal with surface area, we start out by saying what is x prime, like I said, of t, and we already know that's 2t. And then what is y prime with respect to t? We already know that's 1/2 or 0.5. We're using the interval from 0 to 2, and we're revolving around the x-axis. I always think of it as starting with the arc length and then multiplying times 2 pi multiplied times some radius. If we're revolving around the x-axis, then the radius is the y value. So a lot of times in here, I'll just put the y of t notation. And then in here, I'll put x prime instead of f prime. And here, a lot of times I put y prime instead of g prime. That's, again, just notational. For this example, we're going to be integrating from 0 to 2. The function for y is t over 2. Make sure if it has multiple terms, you put in the parentheses so that it multiplies the whole thing. X prime, we already know, is 2t. Y prime, we already know, is 0.5. And so this is my integration. That integration is going to find the surface area that I want, and I can simply plug it into my calculator. And if I wanted to, I could use what we had before and just input and adjust what we had before. In other words, we did the arc length before, so I could do that. When I computed all of this, hopefully I calculated it right and I typed it in correctly, but I ended up with about 17.12. That's after we multiplied by 2 pi. Don't forget to multiply that by 2 pi. So that's the surface area for taking this curve and revolving it around the x-axis. Let's do another example. This next example says the same thing. We want to find surface area, but instead of revolving the curve over the interval from 0 to 2 around the x-axis, in this case, we'll revolve the curve from 0 to 2 around the y-axis. We can go ahead and compute this if we'd like. And in fact, if you want to try this on your own, just push pause on the video. I'll do it in a couple of seconds. So here we go. We've already done the derivatives, but now we're looking at the y-axis. Now, if I'm rotating around the y-axis, I change the radius from a y value to an x value. And the only change is going to be the function that I multiply out front. When I plug this in, the only change from the last problem is going to be the function I multiply out front. So when I set my integration up, I integrate from a to b, x of t, square root of derivative of x with respect to t squared plus derivative of y with respect to t squared, integrated with respect to t, and then multiply by 2 pi. Be careful here. When you put in the function x of t, and we're dealing with a function which has multiple terms, specifically t squared minus 4, make sure that that t squared minus 4 goes into parentheses. If it doesn't go into parentheses, then it'll throw off everything. I just type this into my calculator. When I did that, I ended up with a negative 54.64. Now that can't be the surface area, right? Because surface area should be positive. So we may ask what just happened here. Well, you could probably figure this out, but with the x values that I chose, the x values that we had were all to the left of the y-axis. Since we were rotating around the y-axis, technically my radius should have been the negative of those x values. So I wasn't super clear about that, but that's what, if we wanted a positive surface area, all it would be is the opposite of the negative 54.64, which would be a positive 54.64. But that happened because my x values were negative. And so I got a negative radius every time. If I wanted to combat that with notation, I could just plug in a negative here. But I think instead, I would probably just say, hey, take the absolute value of anything that you get out. And obviously, in this case, it's a 54.64 when I take the absolute value. And that gives me my surface area. This is kind of a neat one. Example 13. If you want to push pause and try it on your own, go ahead and do that. I will give you a couple seconds to try that on your own if you'd like. All right, this parametric set of equations actually gives you a circle of radius 7 centered at the origin. On the interval 0 to pi, it gives you the top half of the circle. Therefore, when we revolve it around the curve, when we revolve the curve around the x-axis, what we're going to get is a complete sphere. So this should give me the surface area of a sphere of radius 7. All right, so let's go through this. We have to figure out the derivatives first. Derivative with respect to t of x is going to be negative 7 times the sine of t. The derivative of y with respect to t is going to give me a positive 7 times the cosine of t on interval from 0 to pi. Since we're revolving around the x-axis, when I look at my equation for surface area, the radius is going to be a y value. Revolve around the x-axis, the distance from the x-axis to the curve will be the y value. So that's what I do. The y value here is 7 times sine of t. Obviously, we're going to integrate from 0 to pi. We get the square root. The derivative is going to be negative. Derivative of x, we said, is negative 7 times sine of t. The derivative of y with respect to t is 7 times the cosine of t. Now, this is something you can actually do really quickly by hand if you want, because when you get this, you get 49 sine squared plus 49 cosine squared. Sine squared plus cosine squared is 1. So you get square root of 49, so you get an extra 7. So you get 49 times sine of t integrated from 0 to pi times 2 pi. So you can do all of this by hand if you'd like. You can also, if you'd like, plug it into your calculator. And if you plug it into your calculator, what you're going to end up with is some decimal version that's about 615.75. If you divide that by pi, you actually get 196 times pi. So there you go. By the way, that 196 times pi is actually equal to 4 times 7 squared times pi, or 4 pi times radius squared, which it turns out is the exact formula for surface area of a sphere, 4 pi times radius squared. So that's an interesting one. We have a nice formula for the surface area of a sphere. Our radius was 7, so ended up that way. It always makes me feel good when we calculate surface area of something and it's something that I know the surface area of and it matches up with what we know the formula should be. Let's do one more. Let's find the surface area generated by revolving the curve around the line y equals 3. And here our curve is x equals 5 cosine t minus 1, y equals 2 sine of t plus 3 on the interval from 0 to pi. Now you can imagine what's going on here. We already know that this is an ellipse, and the center of the ellipse is at the point -1, 3. So we're revolving it around the center, and this is the top half. So this is what you would get if you essentially revolved the ellipse around the middle of itself. Okay, so that's the figure you would get. Now, if you recall, we've already found arc length of this ellipse, and now we're asked to find surface area. Revolved around, obviously, the curve, take the curve, revolve it around the line y equals 3. So what's going to happen is not that much different than what we've done before. Surface area is going to be, it's always 2 pi. This time we're integrating 0 to pi, and then I need to do a radius with respect to 3. If the line I'm revolving around is y equals 3, then the difference between the y values that I'm at and the y equals 3 curve is going to be my radius. In other words, let's move this down a little bit so I have more room to work with. In other words, that radius is going to be my y values 2 sine of t plus 3 down to y equals 3, which is down minus 3. Notice what's going to happen there. If I take this entire formula, the plus 3 and the minus 3 are going to cancel out. And that's what I would get. By the way, I'm getting this inside of the square root because that's what my derivatives were. In other words, x prime was equal to negative 5 times the sine of t, and y prime was equal to 2 times the cosine of t. We did that again earlier, so I'm still using it in this case. So might as well do that. But now if I'm revolving around a different horizontal line, it's just y value minus that horizontal line. So y value minus the horizontal line, and it turns out like this. So we're not going to be able to do that by hand very easily. Therefore, I'm just going to type it into the calculator and see what happens. When I type that into my calculator, oh, be very careful when you do that, as always. Don't forget to multiply times 2 pi out front. Some people forget to multiply times 2 pi out front. And then it throws everything off. But what you would get is about 104.61. It was 61 when I rounded it. Okay, about 104.61. So that would be the surface area of this elliptical shape rotated around y equals 3. And this is how we do those calculations. Again, we have the whole ellipse drawn. We're looking at y equals 3. That is this middle line. I've drawn the whole ellipse, but we're actually just taking from this top half and rotating it around. And so you can see you get some sort of like almost football-like shape. All right, it's an oblong ball kind of shape. So the surface area of that particular shape was about 104.61. Now, these things aren't the only thing that you can do with parametric equations. Obviously, in this section, we did a lot of things. We found derivatives, we found arc lengths, we found surface areas. We found first, second derivatives, slopes of tangent lines came from that. Horizontal and vertical tangent lines came from that. But there's a lot of other things you can also do with parametric equations. But derivatives and arc length and surface area are particularly nice with parametric equations. So that is the end of this section.